is Janet and Rabia.
Welcome to Everest Physics Academy.
Before we start, we'd like to recommend our Everest Physics books for high school,
where you can find more explanations and solve applications and the problems.
In this video, we are going to solve two problems. In the first problem, we are going to explain the self-induction phenomenon, specify the role of the coil, and calculate the value of the self-induced EMF. In the second problem, we are going to calculate the voltage across the coil and the EMF induced in it at T0 equals 0. Calculate in the steady state the current in the coil, its self-flux, and its magnetic energy, and calculate the number of turns in the coil.
Problem 1. Consider a coil of inductance 20 millihenries and internal resistance R. The current carried by the coil varies with time according to this graph. First question. Specify the name of the phenomenon induced in the coil during the time intervals 0.8 milliseconds and 12 milliseconds, 16 milliseconds. The name of the phenomenon is self-induction. But why does the self-induction phenomenon take place during these two time intervals? In the first time interval between 0 and 8 milliseconds, the current decreases. And in the second time interval between 12 and 16 milliseconds, the current increases. So, during these two intervals, the current in the coil varies. So, the coil is crossed by a variable self-flux. Therefore, it is the seat of self-induced electromotive force.
Question number 2. Specify the roles of the coil, generator, electrical load, receiver, or resistor during the time interval 0.16 millisecond. Recall that the coil acts as a generator if the self-induced electromotive force E times I is greater than 0, and it acts as an electrical load if E times I is less than 0, and acts as a resistor if E is equal to 0. According to the graph, I is always positive since the curve above the time axis. Now let's determine the signs of E in the time interval 0.16 millisecond. Let's start in the time interval 0.8 millisecond. According to the curve, the current decreases from 1 to 0.2 ampere during the time interval 0.8 millisecond. So dI by dt is negative. Using the expression of the self-induced electromotive force E is equal to minus L di by dt. L is positive, di by dt is negative, then E is greater than 0. I is greater than 0, E is greater than 0, so E times I is also greater than 0. Therefore, during this time interval, the coil acts as a generator. Now, in the time interval 8-12 millisecond, according to the curve, the current remains constant during this time interval. So di by dt is equal to 0, then E is equal to 0. Therefore, the coil acts as a resistor. In the time interval 12-16 millisecond, the curve showing that the current increases during this time interval. Then I increases, so di by dt positive, therefore E is negative, so E times I negative, therefore the coil acts as an electrical load or receiver.
Let's move to part 3. Determine the values of the electromotive force E during the time interval 0.8 milliseconds and the time interval 12 milliseconds, 16 milliseconds. Let's start with the first time interval. You know that the induced electromotive force is given by this expression, minus L di1 by dt. Now, L is given, but we need to determine the time derivative of the current in this time interval. Look at the curve. In the time interval 0.8 milliseconds, the current decreases linearly with time, so the time derivative of the current is equal to the slope of the straight line. Now, to determine the slope of the straight line, we need to choose 2 points. For example, I will choose this point, okay, and this point. What are the coordinates of these 2 points? The first point is 8 milliseconds with 0.2 amperes, and the second one is 0 with 1 ampere. Now we are ready to calculate E1. The inductance is 20 millihenries. It becomes 0.02 Henry, and di1 by dt is equal to the slope, which is equal to delta I by delta t. So we take I2 minus I1 over T2 minus T1, and be careful, the time must be expressed in SI, in seconds. So the millisecond is converted to second by multiplying by 10 to the power minus 3. And the answer is E1 is equal to 2 volts. Let's move to the second time interval. Similarly, E2 is equal to minus L di2 by dt. And also, we need to choose 2 points, any 2 points on the curve. So we have this point and this point. These 2 points have the coordinates 12 milliseconds 0.2 ampere for this point and 16 milliseconds 1.8 amperes for this point. We are ready to calculate E2. So the inductance is 0.02 Henry, and di2 by dt is equal to delta I2 over delta t, and the points are clear on the graph. The answer is E2 is equal to minus 8 volts.
Problem 2. The circuit includes an ideal battery of voltage UDC equal E equal 12 volt, a coil of inductance L equal 10 millihenry and internal resistance R equal 5 ohm, a resistor of resistance R equal 15 ohm, a switch K and connecting wires. The switch is closed at T0 equal 0. Question number 1. At T0 equal 0. 1a, indicate the value of the current in the circuit. We know that the current starts 0. 1b, apply Kirchhoff's voltage law to determine the voltage UAB across the coil. We start with the voltage across the battery, so UDC is equal to UDA plus UAB plus UBC. But UDC is equal to E, UDA is equal to 0 since the voltage across a closed switch, UAB is equal to the voltage across the coil, and UBC is equal to IR since the positive sense is oriented from B to C through the resistor. But at T equals 0, I is equal to 0. Therefore, at T equals 0, UAB is equal E is equal to 12 volt. 1C. Calculate the value of the self-induced EMF. There is a relation between UAB, voltage across the coil, E, small r, and I, so that UAB is equal to Ri minus E, since the positive sense is oriented from A to B through the coil, but at T equals 0, I is equal to 0. Therefore, UAB is equal to minus E, or E equal minus UAB, which is equal to minus 12 volt.
Focus, please. This is important.
Let's move to part 1d. Deduce the value of di by dt. E is equal to minus L di by dt. Rearrange. Di by dt is equal to minus E over L. We calculated E in the previous slide. E at T0 equals 0 is equal to minus 12 volts, and L is equal to 10 millihenries, which is equal to 0.01 Henry, and the time derivative of the current at T0 equals 0 is equal to 1200 amperes per second. Let's move to part 2. At an instant T1, di by dt is equal to 441.455 amperes per second. Now determine the current in the circuit at this instant. We apply Kirchhoff's voltage law to the adjacent circuit. So we have E is equal to UDA plus UAB plus UBC. UDA is equal to 0. It is the voltage across a closed switch. UAB, the voltage across the coil, we follow the positive sense, so it is IR plus LdI by dt. Similarly, UBC is equal to plus RI. Rearrange. E is equal to I into R, capital R plus small r plus LdI by dt. Now replace each physical quantity by its value. So E is equal to 12 volts. The capital R is 15 ohms, the small r is 5 ohms, the inductance is 0.01 henries, and the time derivative of the current at this instant is equal to 441.455, and the current at this instant is equal to 0.379 amperes.
Part 3. After a certain time, the current reaches its maximum value Im, which is in the steady state. 3a. Determine the expression of Im and then calculate its value. Since the action verb is determined, so we have to start with Kirchhoff's voltage law. E is equal to IR plus L di by dt plus IR. This expression proved in the previous slide, but we know that in the steady state, the current is maximum and is constant. So di by dt is equal to 0. Therefore, E is equal to Im small r plus Im capital R. Rearrange by taking Im as a common factor. Therefore, Im is equal to E over R plus R. Now, to calculate the value of the current, substitute each physical quantity by its value. E is equal to 12 volts, capital R is equal to 15 ohms, and small r is equal to 5 ohms. Therefore, Im is equal to 0.6 amperes.
Part 3b. Deduce the value of the maximum self-flux that crosses the coil, the maximum energy stored in the coil. Let's start with the maximum self-flux. Phi max is equal to LIM. L is 0.01 henries and Im is 0.6 amperes. Phi max is equal to 0.006 webers. The maximum energy stored in the coil is given by this expression, 1/2 Li max squared. L is 0.01 Henry and the maximum value of the current is 0.6 amperes, and the answer is 1.8 times 10 to the power minus 3 joules.
Part 5. The coil carries the following indications. Number of loops is capital N, area of each loop is S equal 40 cm squared, and the length of the coil is small l equals 0.5 meters. Using this expression, L is equal to 4 pi times 10 to the power minus 7 n squared S over L to calculate the value of N. Using this formula, and now replace each physical quantity by each value. L is equal to 0.01 henries. S is equal to 40 centimeters squared, which is equivalent to 40 times 10 to the power minus 4 meters squared. L is equal to 0.5 meters, and now the value of N is equal or approximately equal 998 turns. Thank you for watching. If you like this video,
subscribe to the channel, hit the like button and share.